The rate of energy flow through a unit area perpendicular to the direction of electromagnetic wave propagation is known as Poynting vector. If du energy passes through a cross-sectional area dA in time interval dt, then Poynting vector S can be written as du upon dA into dt. That means the unit of Poynting vector is joule per second into meter square, which can be written as watt per meter square. Now Poynting vector is generally represented as S vector is equal to E vector cross B vector upon mu naught. We can derive this expression for Poynting vector from the basic definition of Poynting vector. Consider a Cartesian coordinate system. This is our x-axis, this is our y-axis, and this is our z-axis. The electromagnetic wave is propagating along the x-axis. Electric field is oscillating along the y-axis and magnetic field is oscillating along the z-axis. Now consider infinitesimally small area dA that is perpendicular to the x-axis. That means this area dA is located in YZ plane. Now the electromagnetic wave travels with speed of light c. So in dt time interval, the energy that crosses this cross-sectional area will travel the distance dx. That means the energy that crosses the cross-sectional area dA is the same energy that is located in this infinitesimally small volume element. Its dimension or its length is dx, that is distance travelled by electromagnetic wave in time interval dt. So dx is equal to c dt. The volume of this element is equal to dA into dx. We can calculate the energy that is contained inside this volume element. This energy we can write as du is equal to u into dV, where u is total energy density. It is equal to energy density of electric field plus energy density of magnetic field. As both electric and magnetic field are present in an electromagnetic wave, energy density of electric field can be written as half epsilon naught E square, and the energy density of magnetic field can be written as B square upon 2 mu naught. Now we play a small trick here. we can replace 1e with CB in the first term, and in the second term we will replace 1b with E by C. So the total energy density U becomes half epsilon naught. We will put CB in place of 1E, so CB into E, plus in place of 1B we will put E by C, so this becomes 1 upon 2 mu naught C EB. Now we know that C square is equal to 1 upon mu naught epsilon naught, or we can write it as epsilon naught C is equal to 1 upon mu naught C. So in place of epsilon naught C we can write 1 upon mu naught C. So the first term becomes EB upon 2 mu naught C. Similarly the second term is EB upon 2 mu naught C. We can write it as 2 times EB upon 2 mu naught C, which becomes EB upon mu naught C. We put the value of total energy density in this expression for energy dU. So dU becomes U, which is EB upon mu naught C into dV. Now we put the value of dV, which is equal to dA into dx. dx is nothing but C dt. So this becomes EB upon mu naught C dA C dt. C cancels with this C and this becomes EB upon mu naught into dA into dt. If we divide both sides with dA dt, then we get du upon dA dt is equal to EB upon mu naught. And we have defined Poynting vector S is equal to du upon dA dt. So this term is equal to Poynting vector S, which is equal to EB upon mu naught. Now since the electric field and magnetic field are perpendicular to each other in electromagnetic wave, so we can write S vector as E vector cross B vector upon mu naught. This is equal to EB sine 90, and sine 90 is 1. So we can write EB as E vector cross B vector. So Poynting vector has the same direction of electromagnetic wave propagation, and it is given as EB upon mu naught.